Let's pick up where we left off with our last video and come back to this discrete circuit representation of a series pass linear voltage regulator. And so what we want to do here is get an equation that relates our output voltage to our raw input voltage and our output current IL. So where are we even going to start with this? Well, we can start by writing a KVL equation that relates our output and our input, so to speak. So what we can do is we can do a KVL along this path here that relates V raw, the voltage across R3, the voltage across our base emitter junction of Q2, and we see at that point we're at our V out. So if we do our KVL along that path, what we would see is that we have V out equals V raw minus R3. So sort of the approach I'm taking is I'm saying our final result V out on the right is going to be whatever we started with on the left minus these couple of voltage drops. So our voltage drop across R3 is going to be that resistance R3 times the total current in R3, which again from KCL we can see is going to be IB2 plus IC1. And so that comes from right here because we have IB2 coming up, IC1 going down, whereas this current was coming in. So from KCL we can see that relationship there. Okay, so we have this is R3 times IC1 plus IB2. And then we're going to subtract the VBE2, and then we're at our V out. So that would be the relationship between those two voltages. Okay, well, we can change this around a little bit. And so let's say we're going to assume our transistors are in forward active mode. So why would we want to do that? Well, we can relate these collector currents to base currents and the base current to collector current, sort of vice versa. One other thing that we're going to assume is we're going to also assume that the current through our voltage divider is negligible. So assume current in voltage divider, and so by voltage divider I mean our R1 and our R2 on the right there. And so what that means then, this second sort of assumption, is that the collector current for Q2, IC2, is equal to IL, because basically we're saying as we come through here, this is our IC2, or sorry, not IC2, IE2. This would be our emitter current, and we're saying that we have essentially zero current coming down this way. And so sort of one other thing we can assume as well is if we're assuming that the base currents are relatively small, of course we can say that our collector current IC2 is approximately equal to our IE2. And so remember, a lot of times with hand calculations we can make these types of approximations. It's going to make our work a lot easier, and it's going to give us a good rough first result. So as I mentioned at the end, there are some simulation results you can look at in the Stephen textbook and see that they agree pretty well to first order. Okay, all right, so we've made all of these assumptions. So what we're going to want to do now is come back and adjust this equation that we got from KVL. So we can say now our V out is equal to V raw minus R3. And now instead of IC1, we can say that that is beta 1 times IB1. And so that just needs this first assumption that we're in the forward active mode. We can also say that our IB2 we can replace with IL divided by beta 2. And so this needs all of these assumptions. It's assuming we're in forward active mode, it's assuming we have negligible current in our voltage divider, and it's also assuming that our base current is essentially negligible and collector current is equal to emitter current. Again, all pretty reasonable assumptions for first order. And then we just subtract this VBE2, which is still kind of just along for the ride at this moment. Okay, so ultimately in our equation at the end, we're going to want V out, V raw, IL, and a bunch of constants. So most of these other things in here are constants, our R3, our betas, our VBE2, but the one thing that we want to address is this IB1. So somehow we want to get this IB1 in terms of these other variables and or other constants. Okay, so just to be consistent with the notes, I've sort of done this out of order in terms of the notes, but let's be consistent and call this equation 2. So now we want to get an equation for IB1 in terms of these other things. Coming back up here at the circuit, we can ask ourselves, how are we going to do that? And we can kind of look at this subset of the circuit right here, and we can sort of consider this to be a voltage divider biasing circuit, and we can use a technique where we get the Thevenin equivalent at the base in order to find our base current. So let's take a look at how to do that. So let's say we want to find our Thevenin equivalent at base of Q1. And so if you want to see more details on this, you can look in Neiman. He has a pretty good description of this, 333 to 334, when he's talking about voltage divider biasing. And so I'll just briefly sketch out the idea here so you have some clue where this is coming from if this doesn't sound familiar. So the basic idea is if we have a couple of resistors like this, and they're connected to our base of some transistor that we're biasing, and maybe we have some other resistors over here. Actually, let me just connect this one to ground. Let's say we have something like that. And so what this is saying then is we can find V Thevenin, so if this is R1, R2, and VCC, what we can do then is we can replace this with V Thevenin, R Thevenin, and something that looks like this. And so of course this is going to make it easier, because now if we want to find our IB, over here on the left side it's not quite as clear, but over here on the right we can just do a KVL around this area here. But again, go check out Neiman if you want some more details, or ask me for questions and I'll be happy to go through that. If we follow this basic approach, what we see is that our IB1 is equal to, we're going to have a messy equation here. So in our numerator, we're going to have V0 R2 divided by R1 plus R2. And so that is our V Thevenin, and that basically just comes from voltage divider at the base. So let me go ahead and, well, let's just do that, and we'll say that is our V Thevenin. And then we have minus VZ plus VBE1, and so those are the other items we get as we do the KVL around that base emitter loop, and all of that is divided by our R Thevenin, which is R1 parallel R2. So this right here, oops, this right here is our R Thevenin. Okay, so let's call this, to be consistent with the notes, equation 1. And so again, I've kind of done that a little out of order compared to what it is shown in the notes. And so now what we want to do is we want to take this equation 1 and we want to substitute into equation 2. So we want to take our expression that we got for IB and we want to put it in for our IB1 up here. So I'm going to show the initial step of that and then skip over a couple of the more detailed algebra steps. You should be able to do this, but the more important thing is that you're able to do the circuit analysis to get to this equation 1 and 2. So sort of just rearranging a little bit, we get V raw minus, and then I can factor out this R3, and I'm going to have beta 1 times a lot of stuff. So I'm going to have V0 R2 divided by R1 plus R2 and minus quantity of VZ plus VBE1. So all of that I've written there is going to be divided by R1 and R2 in parallel. And then we have plus IL divided by beta 2 minus VBE2. And so here's where I'm going to kind of skip over some of the algebra, but again, it's shown in a little more detail in the notes. And if you have any questions about what's in the notes, please feel free to ask me. The basic idea is we're going to use, well, first of all, we're going to split up sort of these two parts inside here. So we're going to split these into two separate fractions, one fraction there, one fraction here, and then we can use what we know about R1 in parallel with R2, our simplified equation for two resistors in parallel is just the product over the sum, and we can simplify that bit. We can pull out this term from our brackets by multiplying by R3, and we can pull out this beta 1 from the parentheses then. So doing all of those things and sort of just rearranging terms, we get to an equation that looks like this. So we have V out plus V out times beta 1 times R3 divided by R1 is equal to V raw minus VBE2 plus R3 beta 1 times R1 plus R2 divided by the product of R1 and R2 times VZ plus VBE1, and I'm running out of space, but I've got just one more term here, R3IL divided by beta 2. Okay, so obviously that's a whole lot of stuff going on there. So what we want to do then is on the left side we can factor out this V naught, divide through by everything that's not V naught, and then we'll have V naught equals. So doing that, and let's see if I can't save myself some writing here. So we'll have V naught is equal to, so we're basically just going to take everything that we had here in the denominator. So let me see, sorry, in the right side is going to be our numerator. So let's just take this, copy, and put that down here. Let's see if we can't just put that right there. Okay, looks good. And then we're going to be dividing that by 1 plus beta 1 times R3 over R1. Okay, so this big mess is sort of the end product of what we were looking at. And so when I'm boxing this, I don't necessarily mean that this is going to be an important equation you'll need on an exam. More just sort of emphasizing our final result here. Okay, so that is obviously very messy and not something you'd want to have to use too often. But what we can see is we accomplish what we set out to. We have basically just constant values in terms of our resistors, our betas, the VZ we see in there as well. And then the only three things that are going to be changing is our output voltage, V out, our raw voltage, V raw, which is our input, and our load current, IL. And so changes in these three things can affect our line and load regulation. And so that's actually the next thing we want to talk about is using this equation, how can we get expressions for both our line regulation and our load regulation? So this is a good place, and so let me spell that better, but this is a good place for you to pause the video and maybe think about how we could use that equation above in order to get our line and load regulation. So of course previously we had talked about these specific equations for our line and load regulation. The problem is for that case we were talking about an AC input and a DC output. Here we have a DC input and a DC output, so obviously we can't use these one-to-one. So we need to go back to what our sort of basic definitions of line and load regulation are. For line regulation, what that is defined as is changes in our output voltage with changes due to changes in our input voltage. And so in this case our input voltage is V raw and our output voltage is V out. So we're saying how much does our output change if our input changes. And so if we look at this equation up here boxed in red, we can think about taking the derivative of this equation with respect to V raw. Well, the only place that V raw shows up is right here. So essentially we get to ignore all of this stuff because it's not being multiplied by V raw, and we're just left with 1 divided by that denominator as a derivative. So we see our line regulation then would be 1, which is the derivative of V raw, and that's multiplied by the constant of 1 over 1 plus beta 1 times R3 divided by R1. So there's the equation for our line regulation, that's simple. So we can do a similar thing for our load regulation. So we need to go back and we need to ask ourselves, what does it mean when we say load regulation? Well, we're talking about how much does our output voltage change with respect to changes in our load current. So of course, changes in our load resistance are going to be reflected by changes in our load current. So again, we come back up to this equation boxed in red, and we say, well, the only place we have IL is here. So now in this case, we get to ignore all of this, and we just focus on this one term over here on the far right. And so if we do that, we take the derivative, we see that our load regulation is going to be, again, we'll have the same denominator of 1 plus beta 1 times R3 over R1. And now in the numerator, we have negative R3 over beta 2. And that would be the expression for our load regulation. And so let's take sort of a minute to think about these two expressions. So ideally, we want to have low line and low load regulation. So ideally, these are small values. So what that's saying is if we have a big change in our V raw coming in, ideally we would want zero change in our V out, but we'll take as little as we can get. So we want that to be really small. And so what we see is if we're talking about line regulation, we have this beta 1 term in the denominator. And so we know that typically beta is on the order of 100. So this is actually a really good thing. So this is good because we have these betas in the denominator. So I'm just going to abbreviate that as denominator. And so we have a similar situation for our load regulation because we still have this beta 1, but we also see this beta 2 is going to be coming down to the denominator as well. So in both cases, we see we have favorable line and load regulation in that both values are going to be relatively small. Okay, so as I mentioned in the Stephen textbook, so in Carl Stephen, on pages 313 to 316, what he does is he compares these results here, I believe it's primarily these three equations, to results obtained using a simulation program. So in this case, he uses a multisim to simulate that. And so what we see is that it agrees pretty well with the hand calculations up to a point. So it agrees well with our hand calculations. The sort of caveat is that this is true while our BJTs are in the forward active mode. As soon as they go into saturation, the agreement isn't so good. But of course, as we set out, we said we're making a lot of assumptions. We don't expect this to be super accurate, but it should give us a pretty good first order understanding of what's going on. And so we see that is true. A couple other sort of design notes to keep in mind as we're considering this circuit is we want to consider our power consumption. So we talked about this is a series pass regulator, and so what that means is any difference between our input and our output power, so our V raw and our V out side, is going to be dissipated in that series pass device. So in some cases we might need to have some type of heat sinking abilities. And so that can take the form of external heat sinks. So maybe we have some type of fins connected to whatever device is absorbing all this power. We'll talk about in our next video about how that's done for IC regulators. Or it could be maybe you have to have some type of fan. One other sort of design note is it's a good idea to test slightly outside of what you would expect your design to be able to handle. And so I'll put in sort of brackets here, just slightly outside. And so the reason we want to do this is because, of course, the real world isn't really going to care if you designed this circuit to work for output currents between 0.3 amps and 1.5 amps. Maybe we have a spike and that's going to go up to 2 amps really quickly. So it's a good idea to to be able to incorporate that into your design process. I'm not saying that every circuit should be able to handle huge amounts of current and voltage, because then we get into that problem that we've discussed earlier in terms of over-designing. But it's probably good to have a little margin of safety when you do your designs.